I'm Gail Tahar, and I lead the therapy ultrasound team at the Institute of Cancer Research at the Royal Marsden Hospital in London. My team has been looking into the way in which ultrasound interacts with tissue, with the aim of looking to see whether we can use it for cancer therapy. The first report of bioeffects of ultrasound came from Professor Wood and Mr. Loomis working in London, and they published in the Philosophical magazine. They were looking to see whether amphibious creatures, so fish and frogs, were killed when they were in an ultrasound beam in water. This paper is a joy to read. I've highlighted here some of their findings. They say that small fish and frogs are killed by exposure of 1 to 2 minutes. An observation also made by Langevin in Toulon with his Poulsen arced oscillator. They did say, however, that mice are less sensitive, a 20-minute exposure not resulting in death, which I guess was good, and though at the end of the treatment the animal was barely able to move, the recovery was fairly rapid. I particularly like the next sentence, which says that blood counts made with a mouse during exposure showed a diminishing number of corpuscles until a stationary state, about 60% of normal, was reached. The biologists inform us, however, that the blood count of a mouse is affected by fear, the corpuscles hiding in the liver until the danger is over. Well, I think we know a bit more about biology now, but at least they showed us that ultrasound could have effects in tissue. Now we know that ultrasound is used to image the baby in utero. We get very nice pictures, either in 2D or 3 dimensions, of the baby before it's born. However, we also know that if we're using the same form of energy, ultrasound, we can blast holes in tissue. This is a rat liver lobe in which we've exposed to high-intensity focused ultrasound, and you can see that there's a considerable amount of damage. We've blasted a hole in this lobe of the liver. So what's the difference between these two? We use ultrasound for diagnosis, as I just said, where we're trying to get tissue information, but without any biological effect. Obviously, in the unborn baby, we don't want to cause any harm. I've subdivided the other uses of ultrasound into therapy and surgery here, where with therapy, I mean we're trying to deliberately produce a biological effect that's beneficial. It may be reversible or irreversible, and we're also trying to get functional modification. So those who do sports may have had ultrasound for their sports injuries, for when they've torn a tendon, for example. At the high end of this power spectrum, we have surgery, where we're trying unashamedly to get cell killing instantaneously. So we want to kill cells with the aim of curing cancer, for example. The difference between these modes of ultrasound usage is the amount of intensity that we use, so the energy crossing unit area and unit time. For diagnosis, we're using milliwatts of intensity, whereas for surgery, we're using thousands of watts per square centimetre. So a factor of 10 to the 4, 10,000 in power. So how does ultrasound work? How does it produce these changes in tissue? Well, broadly, we get a biological change either from heat or from cavitation. If we look first at heat, we know that if we have a beam of ultrasound incident on tissue, some of it is scattered. We need that scattering, else we wouldn't get an image. But only 20 to 40% of the energy that is scattered, energy that is incident on the tissue, is scattered. The rest stays in the tissue and is absorbed, and the absorbed energy leads to heating. So we know that the ultrasound beam, as it passes through tissue, is attenuated. The energy gets less with the distance it travels, and that attenuation is due to both absorption and scatter. Can we calculate how much heat we get when an ultrasound beam passes through tissue? Well, the answer to that is yes. We can use this bioheat equation, which was published by Pennies in 1948. Basically, this equation tells us the amount of temperature rise we get with a given source of heating and a certain amount of cooling. The heating term in this is shown here with Q dot, which is the product. We multiply together the absorption coefficient and the intensity, and that tells us the heating term. That tells us the the way in which energy is absorbed. The absorption coefficient is a function of frequency. The higher the frequency, the more ultrasound energy is absorbed. And different tissues absorb by different amounts. You can see here some maps of attenuation coefficient. Here for a chest, these are porcine chest samples you can see the rib cage. You can see here that the rib bones with soft tissue in the middle. And in the bottom, you can see the absorption coefficient. So you can see that the ribs have a very much higher absorption than the soft tissue in the middle. So here we have 30 dBs for the ribs and 10 dB for the soft tissue. Similarly, if we have cartilage, again, this is another chest sample where you can see the cartilage and soft tissue in between. Here the cartilage is less absorbent than bone, but it's still more absorbent than the soft tissue. Here the soft tissue is absorbing by about 2 to 3 dB, where the cartilage is more than 6 dB. The importance of heating depends on both the amount of temperature rise we get and the length of time for which the heat is held. So we talk about thermal ablation, which is the thermal necrosis that we're trying to get when we do high intensity focused ultrasound. And there we know we have to have 56 degrees or higher and to hold it for 1 second at least. As we go higher in temperature, we can reduce that time. There's another application of ultrasound hypothermia, ultrasound heating, and that's hypothermia, where temperatures in the range about 41.5 to about 48 degrees centigrade are held for long times. So typically 43 degrees for 60 minutes. And it's been shown that if we heat tumours to that sort of a temperature with that sort of a thermal dose, then if we add chemotherapy or we add radiotherapy, then we can enhance the effect of those additive treatments. We know that the amount of temperature rise, the amount of heating we get with ultrasound increases with frequency. It increases with the length of time we expose the tissue for. If we increase the pulse repetition frequency, we put in more pulses per second, then we get more heating. And if we have nonlinear propagation, then the higher frequency content of the nonlinear wave will also enhance the amount of heating we get. The other way in which we get effects in tissue is acoustic cavitation. This is the formation and activity of gas-filled bubbles in an ultrasound-exposed medium. The sort of bubbles that are produced by the ultrasound are at resonance size about a micron at the megahertz frequencies that we use in therapy. The bubbles may oscillate stably. They go into a sort of breathing oscillation where they expand and contract. Or they may undergo inertial cavitation, where they expand far too rapidly. They expand very rapidly, but they can't then continue to oscillate. They expand very rapidly and they collapse, releasing enough energy to damage tissue.